All right. Good morning, everyone. Let's start. So, last lecture we were talking about virtual memory. Am I audible?
Yes, ma'am.
All right. So, we were talking about virtual memory, and we discussed that it is the lowest hierarchical level in the memory. It is the largest, slowest, but it is a storehouse or a secondary backup for all the instructions, program, and data. And then uh, since cache and main memory are volatile but much faster, so every time if you want any process to operate, a sub window or a sub copy of that process, software part is brought into the main memory and then operated in coordination with the cache. So there is a relocation of data that was taking place from virtual memory to the main memory and to the cache. So we forgot about cache because since we've already discussed how cache and main memory are working in coordination, now we had to discuss about main memory and the virtual memory, right? So we discussed that any address that comes from the processor, if it is meant for the highest order level in the largest order level in the memory, it is definitely a virtual address. Remember? Anyone who can tell me what is the difference between a virtual address and a physical address? What is the difference between a virtual address and a physical address? फिर क्या फ़ायदा, मैं अपने आप को पढ़ा रही हूँ फिर तो दिस इज़ माय थर्ड लेक्चर ऑन वर्चुअल मेमोरी. निर्मिति, आर यू देयर इन द क्लास?
मैम जो वर्चुअल एड्रेस होता है वो सेकेंडरी मेमोरी की जितनी कैपेसिटी होती है उसके हिसाब के बिट्स के उसके हिसाब से उसकी बिट्स होती है उसके अकॉर्डिंग.
Right.
एंड जो फिजिकल एड्रेस होता है वो मेन मेमोरी का जो साइज होता है उसके अकॉर्डिंग उसकी बिट्स होती है.
Very good. And now you will tell me one thing, that any address that comes from the processor, can it be a virtual address or physical address?
इट इज नॉर्मली जब वो प्रोसेसर से आता है that is the virtual address, then it is converted into a physical address for searching in the cache and main memory.
Very
And if
good.
the main memory is if there is a miss in the main memory, then the virtual address is searched for in the virtual memory.
Okay, very good. So absolutely right. Any address that comes from the processor. See, आपको पहले नहीं बताया गया था क्योंकि हम सिर्फ कैश और मेन मेमोरी की बात कर रहे थे, तो आपने उस टाइम कंफ्यूज हो जाना था. ठीक है. So earlier we told you only about how cache and main memory are coordinated, and definitely they have to be coordinated using a physical address only, because they are smaller in size and the address that is meant for cache and main memory is physical address only. While any address that will come from the processor, हम कहते हैं एक प्रोसेसर के पास 16 गीगाबाइट्स ऑफ मैक्सिमम मेमोरी है, तो ऑब्वियसली 16 गीगाबाइट्स के हिसाब से ही उसका एड्रेस बिट्स होंगी एंड उसे उतनी ही बिट्स का एड्रेस आएगा. अब प्रोसेसर ने तो पूरा एड्रेस भेजा मेमोरी के लिए, बट द पॉइंट इज दैट वी डू नॉट वांट टू वेट फॉर सो मेनी क्लॉक साइकिल्स, milliseconds, up to secondary storage takes milliseconds to access. We do not want to wait for that time. So what the processor has done is it has maintained an hierarchy, and this hierarchy level, these two, they are much faster. So what it does, it translates this virtual address to a physical address. And definitely we discussed that in virtual memory we have these smaller subsections of the memory called as
Pages.
pages or frames also sometimes, right? Now each of the page, while any program or process is accessed, is relocated and brought to the main memory because it is faster. We don't want every time to wait for milliseconds to get every instruction or data from the virtual memory. So the processor has placed these pages which it is accessing currently based upon locality into the main memory. Now relocation has already happened, and then it maintains a register or a table which was called what? How does it map?
Page table.
Yeah. So it maintains a table wherein for every virtual page number we have a respective physical page number, है ना. अब उसने relocate तो कर दिया, relocation का उसने information भी तो कहीं store करनी है ना, वो वापस नहीं आना चाहता. virtual memory के पास. So what the processor does it stores the this information of a virtual page number mapped to a specific physical page number in the page table. ये हम last time पढ़ रहे थे, है ना? अब now when the address comes, and rather than going to cache or main memory, the first thing the processor does is to go to the page table. So obviously you would want to save on time, no? You made smaller cache and smaller main memory and faster also, SRAM and DRAM, है ना? So you would want your processes to run on the faster ones. You would like to have an optimized speed. So the processor, rather than going to first of all any memory, it goes to the page table, and then I'll tell you how it does. Okay. So in the page table, it sees that for a corresponding virtual page number, we have a specific physical page number. And this physical page number definitely corresponds to what now? What does it correspond to, the physical page number?
The virtual page number in the virtual memory.
The physical page number that has brought in from the virtual memory into the physical memory, है ना? अब मैंने यहाँ से जैसे I'll just take an example now. So I have, say, this is one page, right? I brought this from here to here, and then suppose this the virtual address was 34 bits and my physical address is 20 से 21 bits. Last time वाला example ही ले रही हूँ, ठीक है? अब 34 bits को 21 bits में convert कैसे कर रहे हैं? ये इस table से उसने यहाँ से ये पेज उठाया और उसको उठाकर यहाँ डाल दिया. अब यहाँ डालने के लिए कुछ तो उसने अपने पास भी रेफरेंस रखना है ना, कहाँ से उठाकर कहाँ डाला. सो इट कीप्स दिस रेफरेंस ओवर हियर इन द टेबल, एंड देन just looking at the table, it comes to know what is the respective physical address corresponding to the virtual address for which it was looking for the page it was looking for. Getting? Like, I my name is Amanpreet Kaur. In at my home, somebody would call me something else as a nickname, give me a nickname. And then if a letter comes from somewhere from UGC or maybe a grants commission, and on the letter suppose it's written my nickname, so then my family would be consulted on the address. The postman would come and ask, see whether this person stays here, and then my family would tell me, yeah, she is Amanpreet, but at home we call her something else, right? Are you getting?
Yes, ma'am.
Yeah, so
Yes, ma'am.
on the same grounds, we have a virtual page number, which is the virtual address actually for a given page, and it has a corresponding physical page number, which is a physical address for the same page, and that page number is consulted. And then what should the processor do next? Now you have this. Now you have the physical address, right? So what happens? You have this now. So the page table is consulted, you have the physical address. What should the processor do next? What should the processor do next? Anyone? Look for it in the memory. No? Yes. So this address, where should it be looked for first?
Cache.
In the
Very
cache.
good. Absolutely. This is what I wanted to hear. अब तो वो hierarchical order में ही ढूंढेगा. अब उसके पास physical address आ गया तो सबसे पहले वो cache में देखेगा. यहाँ से मिल गया तो it's a cache hit. No need to go to higher order addresses. अगर नहीं मिला तो it's a cache miss. So it goes to main memory, right? If it finds the respective page from the main memory, it's a page hit. And if it is not there, it's a page fault, right? And then the address will go to the virtual memory, and this means I will tell you how page fault is actually handled. A page fault is a big problem, but just to let you know that it's a page fault right now. Okay? And then if it's not there, it's gone. If it is there, it's a hit, and then the copies are created accordingly. I hope till here is clear to everyone.
Yes, ma'am.
Anybody has any doubt can ask. Okay, so we'll move on now. I just assume that you all know now. Yeah, we discussed this last time, this one also, and this is what we were discussing while the class got over. So we were talking about the virtual memory operation right now. Now, so we were talking that in the first go, when the power is switched from the off to the on state, uh, there is a page miss or a page fault from the main memory, and then the address goes to the virtual memory, and from there the respective page is picked up. And then see, you might have two types of page fault. One, when the page is not there in the virtual memory also, and one when it is not there, not translated from virtual memory to the main memory. I just take this diagram, uh, this one only. See, you can have page fault in two cases. Once, when the page is not translated, है ना? How many entries does a page table have? Anyone?
As the number of pages in the virtual memory.
Absolutely right. So page table की entries होंगी equal to number of pages in virtual memory. अच्छा, will every entry have a respective physical page number?
No, ma'am.
Why?
Because, ma'am, the physical address, the virtual address which is coming from the processor, that only will be converted to its corresponding page table मतलब जो पेज नंबर
ठीक
होगा
है.
उस मेमोरी के लिए, सो दैट क्योंकि हमारे पास बहुत सारे पेजेस होंगे वर्चुअल मेमोरी में, अगर हम सबको कन्वर्ट करने बैठ जाएंगे तो इट विल टेक अ हेल लॉट ऑफ टाइम.
Okay. So just to consolidate all what you said, in the virtual memory, say I right now had 2 raised to the power 34 bytes as the virtual memory size, right? And suppose one page is say 4 kilobytes. How many pages do I have? कितने आ जाएंगे? 2 raised to the power 4 is 12 ना? 2 raised to the power 12. So 2 raised to the power 22 approximately. ठीक है? Now,
Yes, ma'am.
your page table will have 2 raised to the power 22 entries. See how many in number? Such a big one. कितनी सारी स्पेस तो पेज टेबल ही ऑक्यूपाई कर रहा है ना?
Yes, ma'am.
और इस पे every entry has some extra information also. There is a valid bit, there is a reference bit, there is a use bit, there is a dirty bit. So it's a big size. So a good amount of memory is occupied by the page table. Now, if I have 2/21 as the main memory size, 2/21 bytes as the main memory size, how many pages will I have here? कितनी कैपेसिटी है इसकी? कितने पेजेस अकोमोडेट कर सकता है ये? 2/21 divide by 2 raised to the power 12. So that makes 2/9 maximum.
Yes, ma'am.
है ना? समझ आ रहा है ना? ये लास्ट टाइम वाला एग्जांपल ये बच्चे, I have not changed anything. Everyone, is it clear?
Yes, ma'am. Yes, ma'am.
Okay. Now see, you have 2 raised to the power 9 pages in the main memory and 2 raised to the power 22 pages in the virtual memory. Can you map all of them to the main memory?
No.
No, it's a small box. That is a bigger box. You cannot move all the contents from a bigger box to a small box. Right? So at the most, you can just translate 2 raised to the power 9 pages in one go. So even if, you know, the translation is done for all, if we presume that main memory is full, in that case also you can maximum have 2 raised to the power 9 pages, right? Now in your page table, which will be somewhere here, I'll show you one more diagram regarding it. So if I talk about the page table, here only if I talk about all 2 raised to the power 9 pages being translated, 2 raised to the power 9 translated entries. Am I correct in saying that?
Yes, ma'am.
Yes, ma'am.
इससे ज़्यादा तो आप कर ही नहीं सकते ना. So Any address that has come from the virtual memory, which from the CPU as a virtual address, goes to the page table and sees all the entries there. You will have 2 raised to the power 22 entries, but each entry will not be a translated one, right? So just from the page table only you will come to know whether it is going to be a page hit or a page fault. Are you all getting?
Yes, ma'am.
Right. So if it's a page fault of such a case, the address directly goes to the virtual memory first, because it's not there in the main memory or the cache. No, अगर वहाँ वो translate ही नहीं हुआ तो वो आया ही नहीं है. It's very clear. वो पेज वहाँ से यहाँ तक आया नहीं. Getting?
Yes, ma'am.
Yes. So the address goes to the virtual memory, now picks up the page from there, creates a copy here in the main memory, and then replaces one of the block, one of the page here. क्योंकि ये तो full है. Main memory is full. So this means one of the page has to be replaced, and that replacement is which policy now?
Fully associated.
Least recently.
That is placement.
Least recently.
Very good. So last time Ankit was telling me, ma'am, we have something called optimal replacement policies. That is also followed, but right now we are talking about LRU. ठीक है, तो जब वो रिप्लेस करेगा तो लीस्ट रिसेंटली यूज्ड. अच्छा, अगर फर्स्ट गो में जब हम पावर स्विच ऑफ को ऑन करेंगे, प्रोसेसर का पावर ऑफ से ऑन स्टेट पे आएगा, तो उस केस में भी आपका पेज टेबल खाली मिलना चाहिए आपको,
Yes, ma'am.
है ना. उस केस में आप प्लेसमेंट पॉलिसी फॉलो करेंगे. सो इन दैट केस द एड्रेस कम्स and it goes to the page table, and it sees that the table has everywhere has no entry, no translation entry done. It has the virtual page number, but the respective page number, physical page numbers are not there because the translation has not been done. Now no process has yet been opened. Getting?
Yes, ma'am.
Yeah. So in that case it follows a placement policy, and that was fully associated. अगर यहाँ तक क्लियर हो गया है फिर मैं एग्जांपल लूंगी अब. ठीक है, क्लियर है सबको, एवरीवन?
Yes, ma'am.
Okay, good. So this is what we were discussing, that we have this placement and replacement policies. So where can a block be placed in the main memory? We follow in the first go of the placement policy, which is followed is the fully associative, and just in case we have to replace on a page fault, it is least recently used. Now this is where I guess this is where I left. So I was talking about the page table, and this is what I would like to show you now. How to access a page table from the memory. Now see, the address which has come from the processor, this is a virtual address, right? A virtual address gets broken into a page index and the offset, or we can call it as the virtual page number and the offset. Offset is again given as log base 2 क्या होना चाहिए of
Page size.
yeah, and page size of what? Main memory or virtual memory?
Virtual memory.
They are the same. Even if you talk about main memory, your page size remains the same. ठीक है ना? तो वैसे तो virtual memory का reference लिया जाता है. So whatever address that has come from the processor gets broken into two parts. One is the page index or the virtual page number, and the virtual page offset. And offset is given as log base 2 of the page size. Now this address has two parts. I'm telling you how the operation takes place right now. ठीक है? And this address has two parts. Now the page index, the earlier the initial bits of the virtual page number, also known as the page index, are used to refer to something called as page table register, PTBR. So we have a register which contains the address of the page table. Now, as I was telling you, the page tables can be very, very large in size. We can place them in the virtual memory only, We can place them in the main memory, or we can place them in a separate cache. Depends upon whichever is the most optimized policy of placement of the page table. Getting?
Yes, ma'am.
Now, yes. So this page table, so the initial bits of the virtual page number are used to access the page table register, and this register now tells the address of the respective page table, right? And in the page table you have, I should draw it here for you. So we will have VPN number, virtual page number. Oops. This diagram is better, no? Yeah, I can explain it from here. This is better. So if we just see, here, the virtual address gets broken into virtual page number and the page offset. The initial bits of the virtual page number are used to access in the very first go, even before going to the cache, a page table register. From this register, it comes to know that where is the page table currently located. See, you can have the page table located in a cache, which is called as a translation look-aside buffer. It can be an inverted page table placed in the main memory. It can be a normal page table placed in the virtual memory also. सबसे बेस्ट कौन सा होगा?
कैश में.
हाँ बिल्कुल,
Translation.
क्यों हम नहीं जाना चाहते बाकी मेमोरीज के पास. वी डोंट वांट टू वेस्ट टाइम, सो द बेस्ट प्लेसमेंट इज इन द कैश ओनली, but we will discuss about others as well. So the now whatever was broken into virtual page number and page offset, this goes to a page table. So you know where is the address of the page table. You go to the page table, and from the page table, you, for a respective virtual page number, you get a respective physical page number. From that physical page number, the offset is concatenated. What is concatenation?
Suffixed.
Suffixed. Very good. The right term is suffixed. So it is suffixed and the final physical address is formed. अब ये आज सारा समझ आना चाहिए क्योंकि दिस इज माय थर्ड क्लास और मैंने पूरे कॉन्सेप्ट्स आज आपको सारे बता दिए. ठीक है. सो योर फिजिकल एड्रेस इज ppn followed by the offset remains the same. See, the offset does not vary. So since the offset depends upon the page size and the page is the same page which has been brought in from the virtual memory to the main memory, and this is just a relocation of data that has happened. So the physical address will be a physical page number followed by an offset, and this accesses the main memory now, and the data is looked for and we get it. ठीक है, clear है?
Yes, ma'am.
Yes, ma'am.
Okay, very good.
Yes, ma'am.
Let's move back now. Yes, so this is what we were discussing, that we have this page table, and this is a very, this is a data structure which is taken care of by operating systems, but it is very large in size because obviously if we have a big secondary memory. And okay, tell me one thing, can we just vary the size of the page table by doing something? What if my page size increases? For a larger page size, what should be the relation with the number of pages? If I have, yeah,
They
obviously
should decrease.
they should decrease, they should go down. If I have a larger block size, obviously the number of blocks in a room will definitely be less. If I have a smaller block size, which is just the size of a brick, I'll require more bricks to fill in the room. It is on the same grounds. Now, so what happens? We can optimize the page size to vary the page table size also. Okay, just this example we took last time. So if we had 2 raised to power 28 as the virtual address, 4 kilobyte was the page size, and accordingly we had 2 raised to the power 16 as the number of pages in the virtual memory. and hence 2 raised to power 16 entries in the page table. Per every entry, see, if we have to use the page table, then again this is also a data structure, so it requires also some lot of extra information. That extra information can be used bit, reference bit, dirty bit. So that is 4 bytes per page table entry and a total of 256 kilobytes just for a 28-bit virtual address. So nowadays, if we talk about the current scenario, the virtual addresses are quite large in size since we have a big secondary memory, right? So one way of reducing the page table size is to have a, we can have a larger, अच्छा अपनी मर्जी से ले सकते हैं लार्जर पेज साइज, किस पे डिपेंड करना चाहिए? Can we take a larger page size just to suit our needs?
No, ma'am.
So what should it depend upon?
प्रोसेसर एक टाइम पे मैक्सिमम कितने बिट्स हैंडल कर सकता है?
Absolutely, and कितने processes भी handle कर सकता है. So with respect to a process, how much page size is feasible? So this is optimized, and a larger page size definitely leads to a smaller page table size, but then this is an optimized value. We cannot just take it according to our needs. Okay, and then let's talk about the type of page tables which are available. So one would be a normal page table, which will have every time we will have a, you know, a VPN and respective VPN, and then some extra bits for the, you can say the reference and the valid information. You know, this will be the simplest one. Sometimes we use something called as an inverted page table just to reduce the size of the page table. So here we use a hashing function. Anybody who knows what is a hashing function? You should have heard about it. You people are ENC engineers. Data structures पढ़ा है?
Yes, ma'am.
तो थोड़ा तो पता होना. Hashing क्या होता है? Hashing is a specific function that we talk about. Anyone? Okay. So the point is that here, see, normally we go in for, how do we search? We go in for a VPN corresponding to PPN. ठीक है? In the hashing function, something opposite is done. Here, for a respective frame number or the page which is being you know accessed right now, we look for the respective VPN number. तो आपका जो टेबल होगा उसमें सिर्फ वही एंट्रीज होंगी जो ट्रांसलेट हो रही हैं. Are you getting? So there is an access required for a specific page. Only that page entry will be made into the table, not all. So this is a smaller kind of a table which is depending upon, you can say, locality. So only the ones which are being accessed will be entered into the page table, rest all others will not. And since it is working on an opposite function, earlier we used to look for, you know, the entire table and match where can we find a respective VPN number for a given VPN number. So I should say VP number. So N is actually number only. So it's virtual page number. And then इसमें उल्टा होता है. So what we are doing right now is opposite. We are only looking for those entries for which we are currently accessing. Is that clear, everyone?
Yes, ma'am.
Now you can ask me if there's a doubt. अच्छा आप देखिए, I'll give you an example. I have a class of say 200 students, and then I shift 50 to another section. Maybe because I was not able to accommodate them, or maybe they wanted some extra skills, so I shift them to some extra skill classes. And then I earlier I had made a table, I made a register wherein I had the entries for all 200 and only 50 against the ones who were transferred were marked कि इनको मैंने रोबोटिक्स की क्लास में सपोज शिफ्ट कर दिया, तो अब वो मेरी क्लास भी लगाएंगे और रोबोटिक्स की भी लगाएंगे. अब this was a normal page table wherein I would maintain 200 entries and only 50 were translated. Opposite would be I will maintain a page table only for 50, the ones which are translated, and then whenever any address, I mean any notification comes for those students who have shifted, I will just look in to the table which is a shorter table right now, and then keep updating it. I hope it's clear now.
Yes.
Okay, so this is called as an inverted page table. The best one that we talk about is a translation look aside buffer, wherein we place the the translated addresses into a cache which works on locality. So let me come to that. यहाँ तक clear है सबको? Any doubt still here?
Clear, ma'am.
Okay. ये किया है या clear है? What did you say? चलो.
I thought you were talking about till the last slide.
हाँ नहीं वो तो हमने कर लिया. I'm just moving on. मैं देख रही हूँ कुछ शूट तो नहीं कि आपको बताने वाला. Okay. One thing which I told you last time, that with LRU we use an extra bit called reference bit, which keeps a record of how many times a respective page is being accessed, and that is associated with the counter, and the one which is least access is replaced. This I have taught you last time. Just moving on. ये भी हो गया, ये भी हो गया. Yeah. So let's talk about what is a translation look aside buffer. Now, see, the page table is again 2 raised to the power 22, has 2 raised to the power 22 entries, and each entry can maybe take 1 byte extra, 2 bytes or 3 bytes, or depending upon the kind of protection information and the use information required. है ना? So my page table can be very big in size. If I move it to a cache, can I have such a big cache just for a page table?
No, ma'am.
No, again, I'm stuck up with the same issue, that if I have to place such a big page table into the cache and it's going to cost so much, what is the fun of having it? So what we do is we again follow the principle of locality, and only the addresses which are being translated most frequently are kept in a buffer, a cache, and now it is called as a translation look aside buffer. ठीक है? Now, so since the page tables are usually so large that they are stored in the main memory and sometimes page themselves. Yeah, I will tell you about a multi-level page table also. So I'll tell you later on, but let's talk about the buffer right now. And this means that every memory access logically takes twice as long, with one memory access to obtain the physical address and second access to get the data. Therefore, we rely on the principle of locality. If the addresses have locality, then the address translations for the accesses also must have locality. है ना? अगर बार बार डेटा और इंस्ट्रक्शन लोकेलिटी फॉलो कर रहे हैं तो ऑब्वियसली उनके एड्रेस भी तो यूज हो रहे हैं. So we follow locality with this page table also, and this special address translation cache is referred to as a translation look aside buffer, also a TLB or a TB. And a TLB entry अभी आपको आगे बताती हूँ मैं next diagram से. Now see how a translation look aside buffer operates. So we have this virtual address. So we have this virtual address, and it comes from the processor, gets broken into two parts: log base 2 of the page size, a page offset, and the remaining as the page frame number or a virtual page number, right? Then in the cache, so obviously it should go to the cache first, right? So it goes, see, if we are placing the page table anywhere else, it should access the page table register, and from the register we get to note the page table address. If it is not accessing the page table, from the page table register, definitely the address should go to the first cache, and that should be a translation look-aside buffer. Now, here again, the way we used to have protection information with the cache, fast तो नहीं है ना, ठीक है बच्चे? I hope my speed is fine.
Yes, ma'am.
So the way we used to have a protection information for other caches, here also we have a valid bit, we have a read bit, we have a write bit, and then we have a tag, and then we have the respective block. Fine. Now, the address which is broken into page offset and the page number comes to the cache. It starts searching for all tags in parallel after checking the valid information. So what will the valid information tell?
If the cache is empty or not.
Yeah. So if the valid bit is 1, this means the respective tag or the respective block is holding some data. जैसे कैश होता था वैसे ये भी ऑपरेट कर रहा है, बस टैग वाले पार्ट में आपका फिजिकल पेज नंबर पड़ा हुआ है और ब्लॉक वाले पार्ट में आपका फिजिकल पेज नंबर पड़ा है. तो यहाँ वर्चुअल और यहाँ फिजिकल. समझ आ रहा है? नहीं. I'll tell you again. So this is my cache, the entire cache. ठीक है. कैश में क्या क्या होता था बताइए मुझे. We used to have a direct map cache, we used to have a set associative cache, and we used to have a fully associative cache. Yeah, this is a direct map cache first of all. Then the way we used to have, I mean, every cache has the same organization. It has a valid bit, it has a use bit, it has a read write bit, extra protection information इसकी भी रहेगी. फाइन. जो टैग वाला पार्ट है वहाँ वर्चुअल पेज नंबर पड़ा होता है और जो ब्लॉक वाला पार्ट है वहां पे आपका फिजिकल पेज नंबर पड़ा है. ठीक है.
Yes, ma'am.
Yes, ma'am.
अब जो आपका वर्चुअल एड्रेस आया प्रोसेसर से, दिस इज गॉट ब्रोकन इनटू टू पार्ट्स, अ वर्चुअल पेज नंबर एंड द ऑफसेट. द ऑफसेट इज रिमेन्ड एज इट इज, बट द वर्चुअल पेज नंबर is searched in parallel with all the tags. As I told you earlier, tags are all searched in parallel. But then before searching the tag, what should it look for?
Valid bit.
Yes. So the valid bit has to be 1, which means that, you know, the respective page number is translated or the respective page number is there in the cache. Otherwise, it is not there if the valid bit is 0. Okay. So after the valid bit is 1, all the tags respectively are matched in parallel. जिसकी valid bit 0 होगी वो वाली matching ही नहीं होगी, उसकी mapping करने की जरूरत नहीं है. This means it's not containing something. So after the valid bit checking, if it is 1, all the tags are mapped in parallel. The one which contains the respective virtual page number is looked for. So maybe right now they have shown this one. So this is the one which matches, right? And then the respective entries from the respective block, you can say, are brought into a mux. The right one is selected. So there is a mux which has inputs from all the blocks, right? The right one, which is the control, which controls the output of the mux. आप मुझे बताइए यहाँ से क्यों आ रहा है इनपुट, इसकी क्या जरूरत है? Mux, how does a mux operate?
We have multiple inputs and a single output.
Yeah. So I say if it is a 8:1 mux, what is the control logic behind it?
There'll be 8 inputs and 1 output.
And how is the output selected?
AND operation or NAND operation.
Yes. And that AND or NAND will actually give you the output in terms of binary values from 000 to 111. Getting?
Yes, ma'am.
एक्चुअली तो फाइनल कंट्रोल इससे बनेगा, है ना? अब आप देखिए, स्टेप नंबर 1 एड्रेस डिसोसिएट हो गया, स्टेप नंबर 2 वैलिड बिट मैच हो गई, स्टेप नंबर 3 आपका टैग मैच कर गया. टैग मैच कर गया तो जहां से भी जिस भी पार्ट का टैग मैच किया वो कंट्रोल है आपके मक्स का। मक्स के पास जितने भी आपके टैग्स हैं या जितने भी ब्लॉक्स हैं उतने इनपुट्स हैं, पर एक आउटपुट आएगा और वो आउटपुट डिपेंड करेगा आपके रिस्पेक्टिव टैग मैचिंग से। सो विच एवर रिस्पेक्टिव ब्लॉक इज मैच्ड, that is the selected one, and the output of the mux is with respect to that block's data, and this is your physical page number of this block now. अब यहाँ तक समझ आ गया है तो मुझे बता दो, नहीं कोई डाउट है तो आस्क मी। ठीक है?
Yes, ma'am.
So what you have got at the output of the mux is the respective physical page number. What should happen next?
Now it should look for this address in the cache. Then if it's a cache hit, it will go back to the processor, else it will look again into the main memory. And if it's a page hit, then it will go back to the cache and then to the CPU.
Very good. Just before we go on with all this, the final address is this number concatenated with the offset which is brought from here. ठीक है? I hope that's clear. So we had 43 bits of virtual address which is got converted to 34 bits of physical address. So if I'll just see here, the final address which is formed now contains this PPN concatenated with the offset bits as it is. So 13 bits of offset brought from here to here, and 21 bits of your physical page number. So total makes your physical address as 34 bits. समझ आ रहा है ना सबको?
Yes, ma'am.
So the final physical address, after it is formed, then it goes to the next cache, looks for the data over there. So I'll just move on to the previous diagram now. यहाँ तक clear है ना बच्चे सबको address translation?
Yes, ma'am.
Good. And just let me know when the time is over. Numerical एक करना था. Yeah. So whatever address that is formed as a physical address now goes firstly to the cache. If it's found there, it's a hit, else it is a cache miss. If it's a cache miss, it goes here, finds the data here, and then creates a copy in the cache depending upon whether it is a which type of cache do we have, which policy are we following, whether the cache is full, it is empty. I hope you're able to integrate all the concepts now. ठीक है? अच्छा, ऐसा हो सकता है कि आपका ट्रांसलेशन लुक असाइड बफर से ही मिस हो जाए. What does that mean? If I get a miss from the translation look aside buffer, does it mean something?
मैम इट मीन्स कि उसका जो भी फिजिकल एड्रेस है वो भी ट्रांसलेट ही नहीं हुआ है, मतलब वर्चुअल
हाँ,
एड्रेस फिजिकल एड्रेस में
मतलब
ट्रांसलेट
पेज फॉल्ट वाला सिनेरियो है. So in such a case, the page should first of all be brought to the. So if it's a miss here, what should happen? It will not go to cache, it will not go to main memory, it just directly go to virtual memory. वहां से पेज उठाएगा, कॉपी क्रिएट करेगा मेन मेमोरी में, कॉपी क्रिएट करेगा कैश में, और ट्रांसलेशन लुक असाइड बफर में अपडेट करेगा. ठीक है? अब ये भी एक कैश है. So here also some replacement policy will be followed. Getting?
Yes, ma'am.
So we most of the times follow LRU only. If it's clear everyone, I can just move on to one numerical.
Yes, ma'am.
The right policy I'll take next time. It takes some time to explain. We can do one numerical in the meanwhile. Yeah, let's just start solving it. I guess I just have 2 minutes left. So we right now are given a scenario where we have a system which has a 32-bit virtual address. It has 1 gigabyte of physical memory and uses 1 megabyte pages. How many virtual pages are there in the address space? जल्दी से बता दो मुझे. So what is the virtual memory size? What is the virtual memory size?
4 GB.
Yeah, it
4
is.
GB.
It is 4 GB. And then it says physical memory. What is the physical memory size? Is 1 GB.
1
1
GB,
GB.
And the page size is
1 MB,
1 MB.
1 MB. How many pages in virtual memory?
2 की power
ये हो जाएगा 2 to the power 32
1,
है
2,
ना 32
12.
32.
yeah, so it's about 32 divided by 2 to the power 21. 1 MB is so it's about 20 is 1 MB.
20. 20.
20.
Ma'am.
20. So
12.
this makes 2
power
raised to
12.
the power 12. So we have around 4,000 pages in the virtual memory. How many in physical memory now?
1024.
Yeah, physical memory. So this becomes 2 to the power 32 divided by 2 to the power kitna hai? Page size is 20. Yeah, so this becomes 2 to the power 12.
Ma'am, 2 to the power 30.
Ma'am, 2 की power 30.
30.
1 minute. Physical memory 1 GB.
1 GB now.
हाँ, ठीक है.
1 GB.
Just a minute. Yeah. So this makes 2 to the power 10, and that makes around 1024.
02.
So approximately 1,000 pages in the physical memory. Then it says how many bits are there in the physical page number? Anyone who will tell me now. So the virtual address that has come is 2 to the power 32. 32 bits of virtual address has broken down into virtual page number and offset. How much is the offset?
2 की power 10. 20.
Offset हो
Sorry,
जाएगा
20.
page size, no?
20.
Yeah, 20 bits for the offset. है ना? Now, offset plus virtual page number gives you the virtual address size. Virtual address है 32. तो VPN कितने bits का हो गया? 12?
52.
12 क्या हो गया?
Sorry.
है
Yes,
ना?
ma'am, 12.
And PPN plus offset gives you the physical address. Yeah. So this makes how many bits for PPN now? So 12.
10.
The total is
30.
30. And offset is?
20.
Yeah.
So PPN is 10.
Very good. So 10 bits. Absolutely right. I hope everyone is clear with this question now. All right. I guess the time is also over. Let's just stop it. I'll just finish off this one last point left for discussion. I'll just finish it off next time. And then we will start with multiprocessor configuration and cache coherence. That's all for today. I'll be uploading the lectures this weekend. Thank you, Vijay.